Okay, so questions before we get going? And today's going to be a fun lecture, not this part, but the next one. Any questions before we get started? Okay, I'm going to set my alarm this time. Okay, this is what I'm going to do. I'm going to set the alarm so I don't ramble on into foreverness. Yeah, that's the other, or I should put a clock in front of me. That would be the other thing to do. Alarm, that's probably better. Okay, so we will be done at at 10:45. So I'll give a 10:40 alarm and give myself 5 minutes to wrap up. Okay, go. Say. Got it. All right. Well, we've been talking about sensors. Let me ask the audience, what was the most important feature that we had? Let me wait till the end. All right, well, I'll ask it anyway. What was the most important feature of what we did in the first part of this lecture? I mean, the thing that you got to remember forever. That's the part what forever thing do you have to remember in the first half of this lecture?
Noise.
Noise is a big deal. It's always a deal. If it's not a big deal, you're not looking for it. Okay. Fine. That's good. That's good. What else? What's this picture? What's the big deal here on this picture?
There's a lot of stuff in one little teeny chip.
As the world, I mean, things have changed since I was your age, you know. The mixed signal analog circuit designers are reducing the package size and incorporating all the things that used to be separate into a single chip. Now, are the design decisions different? Not a lot, but it is from a packaging standpoint, from a size and footprint standpoint, it's the same. Let's see what else I'm going to say. The other one that that I would probably put in forever is not everybody agrees what accuracy is. Okay, so just like no one believes what bandwidth is. I mean, they believe it, but there's 100 different definitions. There's a lot of definitions for accuracy, which means when you measure it, when you display it as in technical writing, you got to define what it is you mean, how you measured it, and then what the results are. Okay. What is the most important thing about this page? Not about the time of flight sensor, but if you were to characterize this one slide and how it applies to sensors and how it will be important forever, how would you summarize this slide in saying the principles on this slide apply to every sensor forever?
Know how it works fundamentally.
Yeah, you got to understand the theory. Okay, so if you're going to use something, figure out how it works, because understanding the basic principles behind the stuff you use, it's like, why do we teach N-channel and P-channel transistors in EE306? Because anybody who's going to program software for the rest of their life has to know how the computer works. I mean, yeah, and I'm saying you have to understand optical. You got to understand optical physics to the same level of abstraction that you had to understand P and N channel transistors in 306. Okay, I'm just, don't waste all your time. All right, so that's what was the overall forever message of this slide?
You hate I squared C?
Oh yeah, I do. But actually, it's not this slide. The reason why I hate it. There's a slide coming up to show you why I hate it. What wonderful thing about this slide that I love that will serve you well forever.
That you should use logic analyzers to debug rather than brute forcing your way and printing out everything on the serial.
You should use the most sophisticated test equipment you can afford, okay,
Yeah,
to debug, okay? And this is particular one that's probably in your budget, okay? So it's not the only one. They get more expensive than this one. But if you can, get the best test equipment you can afford when you test, okay? Because it really does let you see what's going on. All right. Okay. So we were just talking about this this 9-axis IMU. The middle 3 axes are yaw, pitch, and roll. They're basically airplane terms. But if you stick them on your robot or on your device, they obviously it matters which way they soldered the chip onto the PCB and which way you put the PCB onto your robot. But basically it's a rotational device. In terms of the robot, I could not figure out a reason to use it. On the other hand, the geomagnetic sensor, this is basically a magnetic field sensor. It was kind of cool because you could tell which way was north. And so there was, I don't know if there's a slide for it. Is there a slide for it? Yes, there is. Okay. There is, I think. Hold on. Nope, there isn't. Okay, so I got to say it here. It turns out all these sensors needed calibration, okay? Because that's another thing that's probably a forever thing. Yes, you can download the calibration maps from the sensor, from the data sheet. You can sort of choose a sensor that the manufacturer says is interchangeable, but yeah, your life is on the line. Your reputation's on the line. I think it behooves you to calibrate it anyway. This particular one needed calibrating because of the magnetic fields. The magnets in the motors affected this sensor, so it had to be recalibrated. Again, this is one of the first things I said, and that is it's an integrated IC. It's kind of weird. I mean, I don't know if I've seen this before. It's actually got 2 I2C interfaces. One outward facing to the microcontroller and one inward facing between the chips, the multiple chips that are glommed together to make the 9-axis accelerometer. So you don't actually access this bus, you just access that bus. What's the FIFO good for? Again, my favorite data structure. Yeah, so it's Austin. It's not all about things I hate, okay? Things I love, okay? Those of you that had classes with me before know I love my FIFOs. Why are FIFOs good? When you see a FIFO, you get all excited. It's good design.
They preserve order, and they mean that the microcontroller is not tied down to read specific data.
So it separates the production and consumption of the data for streaming. Okay, so make sure that's in your toolbox. Okay. I don't know. It's but here's another thing that happens in all of these, in the more sophisticated sensors. Some of these are not simple, okay? There's 117 different registers inside this chip that you can program, okay? what does that mean from you in terms of complexity?
Quite a lot of data sheet to read.
A lot of, yeah. And so this goes back to the thing we did at the beginning of lecture last time. What's the most important thing you need to choose this sensor? You're not looking at the data sheet, I promise you. If all I give you is the data sheet, you're not getting this thing to work. Not with
Reference
117.
design.
What?
The reference design.
Yeah, the reference designs. All right. So I'm showing you these sensors because there are reference designs in your starter code for the MSP432, by the way. Okay, this is why I hate I2C. This will be in the next chapter, but there are, when you communicate when you transmit data from module A to module B, okay, there is an encoding step where the information is encoded in terms of energy. Energy is the object which is transmitted across space, right? This is a distance. And then obviously there's a decoding stage over here where the information is decoded back into light. So you've got some sort of information. In this case, we got zeros and ones, and over here we got zeros and ones. And the way I2C works is it's open collector or open drain with a passive pull-up, and we saw over and over again that that those in the actual implementations on the two devices that I got from various places had a 10K pull-up. Okay? Had a 10K resistor pull-up on the line, in particular on the clock line. So you notice that when it goes from 1 to 0, what can you tell me? This is an oscilloscope tracing, obviously. When it goes from 1 to 0, how do you describe this edge?
Well, that edge is going to be really sharp.
Why?
Well, because on either side of an I2C, the way that they're doing that is they're connecting the system directly to ground through the transistor. They have the dump. I forget what it's called, but yeah, it's basically dumping the whole thing to ground.
Yeah, so you got an N-channel driver on the line, right? That's this pin right there, right? You got an N-channel MOS transistor, which is active, and therefore it can, its conductance is very high, and so its current abilities will be very high, and the speed will be very fast, okay, because it's active. Okay, what about this edge here? The 0 to 1 edge.
Pretty slow.
It's slow because you have capacitance in the signal in the system, and the ability to pull it high is a function of the resistance value 10K. Okay? So, and the way the system actually, there is a thing called clock stretching, which the slave could drive the clock low to stretch the time. This is not clock stretching. This is how I2C works. The master drives the clock low, okay? And then the master stops driving the clock right here. The master stops driving the clock low, and then the master waits for the clock to go high. And then once the clock goes high, it, does a little bit of delay, and then it repeats. Okay? So
where does the capacitance in that wire come from?
From the CMOS circuits. This obviously is connected to the gates of other devices. So it's typically the gate capacitance on the input. And this is a bus. Remember, this clock is tied to all the pins, right? You remember this guy here is tied everywhere. I don't know, was there a picture of it? No, there will be a picture of it. Okay, sorry. Maybe, no. It's a whole bunch of things tied to that line. That's a clock. You know, depending on how many devices you've tied, all of these I2C things are tied to that same line. Yeah,
so if you wanted more power than on your I2C protocol, couldn't you just put get a lower resistor value?
I mean, if you look up I
like
squared,
a 2K.
Yeah, that's absolutely correct. So if you look up I2C and you say, if you want to go, this is the fast rate. If you want to go fast, use a 2K resistor. Yeah. Somehow nobody read that part. So both boards that I've had that are here in this, I use 10Ks.
Maybe it's lower power.
Well, sure, it's lower power, but that's something you already know. How do you make things lower power?
Put less current in it.
Less current. How do you make things less current?
Put a bigger resistor in it.
No, slower. It's always a speed power trade-off.
Okay?
Dr. Valvano, 2 comments. One, is this because you had it hooked up to an oscilloscope with like a 1 megohm impedance because your logic?
Great question. No, well, I don't know. It turns out, where'd it go? Turns out I get the same answer when I hook it up to my, so Austin is bringing up a very interesting thing. There is a capacitance in the probe itself. Okay. But I measured this time 3 ways. Okay. I measured it with the oscilloscope. I measured it with the logic analyzer, right? And I also measured it with nothing hooked up to it, and I have the timer. So I instrumented I couldn't believe it. I thought it was broken, right? I mean, I programmed it for 400 kilohertz, but I only got 300 kilohertz. So I figured there was some more software delay somewhere, right? That I had a software bug.
And the other comment is, can you buffer these clocks or buffer these signals to get better performance?
Use a CAN controller. Okay, it's a nature of the protocol, and that is all of the devices need to be able to drive the clock low. All the devices need to drive the data pin low. So all devices on the bus need access to driving it low. And you will find that as you try to go faster, you can have shared clocks, like I said, like CAN, like Ethernet, whatever. It's just that they use it. And let me just go back to my my definition of energy in the context of I2C. Where is the energy? Well, first of all, what's the equation for energy? In terms of parameters that are shown here on the slide. Electrical energy.
Voltage times current.
Yep, getting there. Voltage times current. One more. That voltage times current is power.
Oh, yeah.
1/2 CV squared.
No. Maybe yes, Austin, but I just not the one I'm looking for.
Just time. How long
Time, sure. Delta
you're
T.
using it.
Yeah, so this time here. Right? Okay, so let's do the first interval. Okay, how much energy is being transmitted?
First interval,
Yeah, right here, this interval right there.
zero, no voltage.
Zero, there's no voltage. Okay. How much energy is being transmitted here? Now, it's not quite zero. There's a little bit of current, but the current is very low, okay? So you have no energy there and very small amount of energy here. This is why I2C don't work, is it never actually generates energy. And so you've heard this. Have you heard that term, NRTZ? Ethernet has it, CAN has it, RS-232 has it. Okay, stands for non-return to zero. So electrical protocols that don't use zero as one of the encodings. In other words, it never returns to zero. Satisfy the energy it always goes from like, plus, plus 6 volts to minus 6 volts or whatever. Okay? So yeah, get out your scope and see. Well, if you're using I2C, a scope is actually also your friend. And yeah, absolutely, this should have been 2K. All right, I don't want to spend a lot of time on this because this is not 445L, but they're I2C when there's a complicated device you're interfacing with, there are often two addresses. The first address is used to select the slave, and the second address is used to select which of those 117 registers inside of the chip you want to access, and then you're going to read or write that data to that address. And these are all write operations. So it's a slave address with a write, and so you send it 1, 2, 3, 4, however many bytes you want to send. If you want to read, basically the read is often 2 steps. The first step is you will write the slave address, which activates one of the slaves. You tell inside the slave which address you want to access, and then you restart a second protocol. There's a stop bit right there. You restart, send the address again with a read. Okay. And then you read as much data as you expect. And as we saw, the last read is a negative acknowledge. Okay, I still don't want to talk about it.
Is this device dependent? I mean,
Oh yeah, totally. Every device is different, but it turns out the ones that are on this page actually all work kind of like this. So I would not say that this was a general thing, but this is a common protocol for interfacing with complex I2C devices. Yeah, it's again, we talked about the triple toggle technique, right? What does the triple toggle technique allow you to do?
You should see on the scope.
Yeah, what 2 things can you see on the scope? Okay, zoomed in here, this is now in milliseconds, right? Zoomed in and zoomed out. What do you see?
the duration of the interrupt.
Yeah, this is the duration of the interrupt, 880 microseconds, okay? Because this is the time, this is time A, this is time A and B, and that's time C, A, B, C. Okay, so the duration between B and C is 180 microseconds, but right here, you have A, B, C so close to each other that you can't visually separate them. So you see the difference between ABC to the next ABC. And again, this is a once your system gets more complex, you want to see how much processor overhead did I use up. An interesting thing that I've seen, I have not done it because I'm too lazy, but could you set this up? Okay, how could you recover? Yeah, I'll ask that as a question. How do you recover that 8% overhead? Because that's not small. Maybe not in this chip, because I don't know if it can do it.
Interrupts.
Could you potentially use interrupts? Okay, so to recover it, you can use DMA. And so basically you set it up as a DMA channel, say go, and then you get an interrupt right here. And you read the data. Okay.
How much benefit do you usually get from using the DNA? Because it still use the bus, right?
It's still
use the
gonna,
data
okay, oh,
bus.
interesting. No, not really. Look, okay, so let's go back to this. Where's the, yeah, that. All right, so this is whatever, this particular one, this is a different sensor, by the way, but it takes 400 microseconds. This whole thing takes 400 microseconds. Okay. How many DMA cycles is this going to require?
Six.
6.
Well,
Just
well,
number of
12,
bytes, right?
12, right? There's two. These are, this is the whole thing, right? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. 12 DMA cycles, right? So depending upon how your DMA is implemented, if it's doing a, well, it obviously has to use the bus. Except, on, if you got some, okay, I don't even want to talk about it. Okay. On the Cortex-M, which bus is it using? Okay, skip that. Okay. Which bus is it used on the
The
Cortex-M?
data bus.
The data bus. Okay. What bus is was the software used to execute?
The instruction bus.
The instruction bus. So they're separate buses. I'm just gonna do a blank slide. On a Harvard architecture, like the Cortex-M, uses the iCode bus to fetch opcodes, and it uses the system bus to fetch I/O devices. The RAM is also on here, by the way. So a DMA cycle would go either into, out of RAM, or into and out of the I/O device, separate from fetching. So DMA is probably, for even 12 cycles, is not that big a deal. But even if you did have 12 cycles, it would. All right, let's go back to, yeah, again, this is not 445L, but let's just, the point is you want to be able to, when your system gets more complex, figure out where your bottlenecks are. Because if you want it to run faster, there are certain things that will make it run faster and certain things that won't, right? Like that 2K resistor will make it run faster. Oh yeah, there's my calibration curve. I did have to calibrate it. Bunch more sensors. There's a thermometer. A lot of microcontrollers have thermometers in them. It uses a transistor, bipolar junction transistor, to convert temperature into some sort of current. Obviously, they're very nonlinear, so you're going to need internal to the device is some linearity circuits. A lot of these, you know, this one you can tell is not very complicated, but this is a humidity sensor, which also has a temperature, relative humidity sensor. Again, this is very vague. I don't know what plus or minus 3% means. Yeah, you have to be fairly. But nevertheless, this one's cool because you can adjust sampling rate and resolution. So what can you do if you slow the sampling rate down?
Higher resolution.
Yeah, you can do more more filtering and lower the noise. Okay, and improve signal to noise ratio. So slow the sampling rate, more filtering, better signal to noise ratio. Okay, or faster sampling and less filtering and more noise. You know, either way, it's adjustable. Here's an optical sensor. This one's kind of cool because those of you who also know what one of the things that Valvano hates is floating point. But this is probably an example of something that actually requires floating point, because to use fixed point, you have to know the range, right? Like over here, right? The range goes from, okay, let's go to this one. The range goes from -20 to +50, right? You have to know the range, and the range has to be small. Okay, and then you can use fixed point. Okay, you know, basically the value is some integer times some constant. That's fixed point. But in this sensor, the range is very large. Okay, because light can either be very dark, a little bit dark, a little bit more dark, a little bit more dark, and so there are many, many, many orders of magnitude in the possible values of the light. And so it comes out as a floating point number, sort of basically a mantissa and an exponent. Okay. I don't know, I think maybe to the 10. Comes out as a floating point. This is an appropriate spot for floating point. There's a couple of Hall effect sensors in the examples that that are in the checkout. There's a tachometer on that robot for getting wheel turns, and basically there's a sensor in here that can detect magnetic fields. And so as this something magnetized comes across, you get basically a digital signal here. You get a digital signal depending upon the magnetic field strength. We use Hall effect sensors. Why? Anybody know why? Basically, it can measure the presence or absence of a magnetic field. For instance, if I'm measuring wheel rotations on my why do we like Hall effect sensors?
Feedback.
Oh, well, we like sensors because they're feedback.
I mean, like for stepper motors and things like that.
Yeah, but why we need? Okay, I didn't ask why we need feedback. What special powers does a Hall effect sensor have?
Can
In
it measure
terms of-
current?
It's what?
I thought Hall effect sensors could measure current.
I know they can, but this one is measuring the presence of a magnetic field.
It's very digital. I mean,
It's digital, fine. Listen, I'll give you that.
that's good, right? I don't have to condition it.
It has no mechanical friction. There's no contact with what you're measuring. Friction. Yes, I'm sure you can use Hall effects for something else, but this one here is for measuring the presence or absence of a magnetic field. So you put a permanent magnet somewhere on the shaft and it doesn't touch anything. And then you measure the presence or absence of that magnetic field as it spins. And you get a beautiful digital signal.
How do you prevent that magnetic field from interfering with other stuff? Like
It's
in our
very small and
445
tiny.
robot,
Yeah, it's very
Are
small
you-
and tiny. It's not very big.
in our 445 robot, like the motors
don't.
of I squared C.
Okay, so
Do you know the reason?
okay, I'm you ask the question again. First of all, you don't. These do interfere, but the magnet you put on the wheel for the tachometer is so tiny it doesn't go very far. And what was your question again?
So, like our motors for our 445M robot, whenever they spun up really fast, they like drop the I squared C line. Is that just because I squared C is like sucks, or is that the
Ooh.
reason?
Your motor.
Yeah. So if we kept the
robot
motor,
drive. Okay,
Oh,
yes,
C.
sure. So that's probably noise pickup. Yeah, that's probably noise. That's probably noise coupling. Because what else happens? Oh, it's gone. The figure's gone. But I'll draw it again. I'll draw it again. What does a magnetic field do to this? Induces current, does it not?
Yeah.
Yeah. And so that's a 10K impedance, which can produce a fair amount of voltage change on a magnetic field, as opposed to a push-pull. The same magnetic field. And obviously it's only going to cause noise when this thing is off, right? When this is off, noise
Yeah.
can come this way. Whereas if you had a push-pull and you added noise to this, the conductance, one of those is on at all times, producing a low impedance path to ground or to 3.3. And so this is not very susceptible. That's the whole reason CMOS was designed, okay? That's so we can walk on the moon, right? CMOS was designed to be radiation, field insensitive.
But that's not how I squared C works now.
Yes, it is. This is an I squared C pin.
No, CMOS isn't, right?
No, CMOS, I squared C is not CMOS.
Yeah.
So I squared
So-
C is half a CMOS. It's just an
So how do you
M.
fix the 445M problem?
I have no idea. Geez, that's Gooslauer's problem. Don't use I squared C.
What if the chip only has I squared C?
Yeah, then you okay. So I think now
from a
to answer your actual question, we have bought, and it just turned out that the plague showed up and we never had a chance to deploy it, we bought this I2C time of flight sensor for Gooselauer's 445M. And at least in the robots that I have, this guy is very robust. It runs for hours without crashing.
Cool.
Yeah, and it has three directions. So I think this is my solution to, but I haven't actually tried it on a 445M robot yet because of the plague. But that's
Oh, okay. Well,
Yeah.
it may mess up. Like, so like from a design standpoint, not 445M, do you just change the chip at that point?
yeah, or you shield it, or you drop the resistor down. I don't know what resistor value you're using. Right, because it turns out changing the resistor value would also affect the noise immunity.
Mhm.
Yeah, there's a reason I don't like I2C. It's because it works in this environment and it doesn't work on other environments. But you can see this whole slide is full of I2C crap. All right, where was I? Yeah, sensor, yeah, we're talking about. Again, there's a different protocol, but it's got the same structure. Yeah, I don't, yeah, again, yeah, when you read a whole bunch of bytes, you send a negative acknowledge at the end. Again, this is doesn't look the same, but it is the same. And basically you send a slave address, a register address, and then you do a start again. A start is a restart with read write equals 1. And then you read the data. Yeah, this is here's some more sensors. This is the one that's on the fitness device. The accelerometer for it is analog, so it's not that complicated. The microphone on there is analog, so it's not that complicated. The light and temperature sensors are I2C again. There's a joystick, which is analog, so this is a much simpler sensor board if you want some sensors and basically don't want I2C. If you want to buy something, I don't know if you've ever shopped, get bored and you get on the internet and want to buy stuff. Seed makes a sensor suite. And depending upon your microcontroller, you either get an Arduino board, or in this case, a TI, a booster pack board, and you can, without having to actually wire anything up, you can buy yourself a set of, get yourself an adapter board, buy yourself the cables, and just instrument up your stuff however you want. So it's a combination of I2C, analog, digital. They have a bunch of different protocols depending upon which one of these connectors you've plugged it into. Okay, so what's next is the fun stuff. Any questions on that? So again, in summary, learn how it works. The sensors aren't all the same. And it's not necessarily going to show up on the exam for this class, but digital signal processing is an awesome thing that you probably want to put into your toolbox. Okay. All right, now we're going to do the fun stuff. Okay. I had fun. Okay, good. Let's see. There's a little bit of this sensor fusion in the book. I think it's later in the book. This is an example of something that I didn't necessarily take a lot of stuff out of the textbook for. So when you study for the exam, you'll have to study. Anyway, there is a sensor. They call it sensor fusion. Edge computing. It's near the end.
What's the exam gonna be like since we're
Oh, I have
online?
no idea.
Not
No
not the
idea.
questions, like the format.
Oh, I know. Oh, yeah. No, I will. I like Gradescope, and so you will probably create a doc file. I'll give you questions. You'll create a doc file. You can either handwrite on your doc file or whatever. Save it as a PDF and upload it to uh, Gradescope.
Is it like one of those grad tests where you have 24 hours or no?
I have no idea. Hey, come on. Yeah, I'll work with you on it. Okay. All right. I
Okay.
promise I'll let you in the loop, but not today. I've been waiting to teach this. Okay. I'm going to wait to do this lecture. Okay. All right. We just did a section on sensors collect information. Okay. This next chapter, this next section is how does software make decisions based on sensors? And when you've got a single sensor, it's fairly simple. You just look at it. But what if you got a bunch of sensors that aren't the same type, aren't the same in units, aren't the same, they don't work the same. Yeah, but you want to look at all the sensors and make some sort of decision based on the collection or the integration. Yeah, like I said, the other name for this in the world of engineering is fusion. Okay. And we're going to look at 4 different ways to do that. Okay. I bring this up. This is in one of the sets of kits. It's called the lipstick, and it has a whole bunch of sensors on it as well. The same sort of ones we've been talking about, but I did not explicitly show you that one. But the ones that we did in the previous section either were generated by this guy, or that guy. Okay, so that was a review from a couple of seconds ago. So let's start with math. The first thing we can do in the field of sensor integration is learn some math. Okay, and yeah, this is going to be on the test. I mean, this is not central limit theorem. Is basically some assumptions that you must make, and that is you have a set of samples, set of collections of measurements, if you'd like, that are identically distributed. Okay, and when I say they're identically distributed, that means they have the same units, typically measured from the same sensor, or at least from the same sensor type. Okay, and so in other words, all of the measurements have the same mean and standard deviation. Okay, so before I go on, what does mu, in the context of a measurement of a sensor, if I tell you that the mean value is mu for this collection of n samples, what is mu? What does it mean intuitively?
It's the true value.
It's a what?
The true value.
The true value with the following assumption, and that is the distribution is not biased. Okay, so if your calibration curve, if you've calibrated a device, okay, then the mean of these samples will be the true value. But what if you didn't calibrate the device? What's the mean? It's not the true value, something else. Okay, so the assumption here in Valvano's world is you calibrated that device, so mu is the truth. Okay, all right. What's the standard deviation of these samples? What's it mean intuitively?
Noise.
That's the noise. Great. All right. So I'm getting back to the central limit theorem. This is why this is kind of interesting, okay? That all the samples are independent, okay? we saw with that time of flight sensor that the samples were not independent, that they were dependent on temperature, and so, or dependent on time. But in this world, we're going to assume that all the samples are independent of each other. Okay, so in other words, knowledge of the prior sample does not give you any more information than the other. If you remember, that plot looked like this, right? It would look like temperature versus distance versus time. On that time of flight OPT 3101 look like that, which means if you give me this sample, I have some knowledge of the next one. Okay, that's dependent samplings. But assuming there's and the other thing that people typically do is it doesn't work really for small n's. It's really defined as a tendency as n gets large. Right, so then to use the central limit, we're going to take the average, the sample mean, not the statistical mean. So from what does it mean, Valvano? What is this? If these are digital samples, what is this equation? It's got a fancy name in the world of software. If I take n samples and I average them together, what have I just done?
You've sort of done an average filter.
It's a filter. Yeah, this is a digital filter. It's a low pass filter. Okay. And you can write out its frequency response and all that sort of cool stuff. But that X bar is a software calculatable digital filter. Okay. All right. So as n gets large, the expected value is mu. What does that mean? That has some really cool consequences. The expected value of that output of that digital filter becomes what as n gets large?
The true value.
The true value?
The true value, okay? Assuming it was unbiased, right? Assuming that you calibrated it. This one is equally cool. What does that mean? The standard deviation of that average is sigma divided by the square root of n. So what does that become as n goes large?
It drops to 0.
Drops to 0, which means you get the right answer with no noise. Okay, that's the cool part. The fact that this this becomes normal is kind of interesting, but not okay. So this is the plot is a probability mass function, which means the the A to D constant voltage was put into the A to D converter, was measured 1,000 times, and this guy here was with no digital filter. This is with a 2-point average, 4-point average, 8-point average, 32-point average, and the point is the take home of this is the standard deviation gets small. Okay. The standard deviation gets small. And okay, the central limit theorem just goes normal, right? The red one clearly isn't normal. The gray one isn't normal, but as n goes large. So that's the consequence. So now we're talking about sensor fusion. So let me remind you, what did you decide what sigma was? Right? Just to remind you before I get to the next slide, sigma is the amount of noise. Okay. So if I were to have multiple measurements of the same information, okay, distance to the left wall, measured with 3 different sensors, the OPT EE382V3101, they ping ultrasonic transducer and one of these sharp infrared analog transducers. But they all have the same units. I measured it 3 ways. One thing the central limit tells us to do, that adding things together is a good thing, okay? The signal to noise ratio of the average of these 3 samples, now they're not averaged in time, they're averaged in method, okay, will improve signal to noise ratio. But we've already mentioned that sigma is the amount of noise, and you might imagine, even though they all have the same units, they all don't have the same noise, okay? And so if you have multiple sensors with the same units, measuring the same thing, but have different confidences, okay? And one of the, we already ascribed to the standard deviation as a confidence measure, a confidence parameter, whereas a small sigma means it's more reliable and a big sigma means it's less reliable. In other words, if it were normal, the probability that you're within 2 sigma of the mean is 95%. Okay, so the smaller the sigma is, the more confident you are. And so one way to integrate or fuse data together measured with the same units of the same thing is to use the standard deviation as a weighting factor, okay? So these are the individual weights weighted by the standard deviation of those 3 sensors. And obviously this is just to get the units to work out, okay? So if one sensor is more reliable than the others, it has more weight, right? So again, a low sigma is an increase in the weight. Okay, and that's a very simple equation. There's a whole bunch of mathematical things that follow this same principle, and that is look at what you find some measure of confidence and use it to fuse the data together. And because this is an IoT class, I'm not a math class, I'm not gonna present them, but if you search sensor fusion or search some of these terms, you will find that it can be used for this same type of thing. All right, that's the first one. All right, okay, I got 3 more. All right, yeah, here we are, 319K again. Everybody loves 319K. Well, I do. I love 319K, as you know, I do. And this was your traffic light or your stepper motor control or whatever you had way back in 319K. Finite state machines are a wonderful way to take inputs and produce outputs. It's an abstractive method. It allows you to visualize the behavior of the system, in ways that are separate from C code. Okay, so it has those beautiful things. And as you remember from 319K, a state is what you know or what you believe to be true. Okay. And so the knowledge, the memory, if you'd like, of a state machine is embodied into what state you're in. Okay, every state in 319K had an output. You wrote that output to a port. Every state had a dwell time. You weighted that dwell time. Every state had exactly the same number of input patterns, right? 0, 1, 2, or 3. And that input determined the next state. We had a little fun sort of thinking about how you would recover the wasted time and the weight. And that is running an interrupt service routine where you do the same 4 things, except you do them in another order. You input, go to the next state, depending on the input, you output and delay. Okay, the boring stuff, okay? So this was our structure here that we used to implement the 319K style data. But now what I want to do is integrate sensors together, okay? And so if you think of a more general approach, Okay. The question is, how would you describe this arrow? Okay. We want to look for a way to describe that arrow. If I'm in the go state, and if the tack used to be above, used to be above 1 RPS, and the bump is not, the bump sensors are not 3F, that means I've collided. So I'm going to go to the collision state and see I've combined tachometer data, which has got units of RPS, with bump data, which is Boolean. Similarly, if I'm in some state, I will go to the off left state if the left sensor is below this and the center sensor. Now here, the two sensors that I'm fusing have the same units. But I don't have to. I can do the line sensor has got this value and the sensor is above that value. Okay, so those are and arrows. In other words, they collect multiple sensor information, and this arrow is an and. Okay, you can do it with or. Okay, again, you can define a collision state. You will go if you're in the go state. You're going, and the acceleration in the y direction, that's the forward and back direction, is above some number, or the bump sensor is off, you're going to go to the collision state. Okay? The danger state, if the temperature is above 40 and the light is above 1,000. Okay, again, you're using the and and or operations, because if you think about an arrow, right? What is it? What is the functionality? What is the behavior of an arrow, right? So if you're in a state, right? If you're in state A, okay, you're gonna go to state B if the inputs are something. If the inputs match some pattern, right? So what is a general way to describe that? What is a general way to describe this condition? I don't want to, in the 319K world, it was, does input equal 1? Okay, does one port value, the value of the switch is exactly equal 1? But how do I ascribe all of this kind of behavior in a single method, a single process? I could get out, I could create my own language, if you'd like, and implement this exact, syntax. But how else might I implement this? How would I implement that in code? I lost you. Are you there? You're just bored?
I mean,
How do we implement that in code?
wouldn't you just use an if statement?
Okay, but I want to put it in the state graph. I want to put it in here. How do I put code in the state graph?
Get the function pointer.
I'm going to have a function pointer. Okay. I'm going to describe this arrow with some sort of function. Okay. What can you tell me about all of the arrows? All of the arrows coming out of the state. So if you got function 2 over here and function 3 over there, what can you tell me about those 3 functions? how would they related to each other or whatever?
They OR to 1.
There ought to be at least one of them that's true, okay? Or your machine will crash, right? But do they have to be mutually exclusive? Okay, so the pointer, okay, there's the function, okay? There's the function pointer. Now you could pass in the inputs if you wanted. I chose not to, just for simplicity. These functions, the F1, F2, F3, have outputs Booleans, yes or no, right? And in this particular system, each state is going to have 10 functions, and function 0 is associated with the index value here, state 0. So these two are correlated. So if function number 5 comes up true, I'll go to, oops, that's a mistake. Ooh, typo. Sorry. No. I don't want a pointer. So, okay. If function number 5 is true, I'm going to go to the 5th element of the next state, and that'll be my next state. Okay. But do they have to be mutually exclusive?
Not necessarily.
Not necessarily, because how are you going to implement it? You can't call all the functions at the same time unless you've got some sort of, FPGA implementation of it. You're going to execute the functions in sequence, and the sequence of the functions in this list will define the priority of one possibility over the others. Okay. How do you specify a variable length? Some states might have one test to do, one function to execute. Some might have 2. Some might have 10 or 9, I guess, in my case. How do you define the length of this array? 2 ways to do variable length array. What are they? Well,
Store the length in the array.
I could store the length in the array. I didn't do it here, but if you, oops, come back here. If I added a, I could add a parameter that is the number of input functions. Okay. 0 input functions might mean stay in the same state, I guess. I don't know. 1 input function probably means always go there, right? So, all right. Okay. What's the other way?
0 terminate.
Yeah, I can sentinel this list with a null pointer. Okay. And again, in 319K, you had a single value, which was the output. And you wrote it to a port. To be more general, you could have a function associated with each port, and then in that function, it could do whatever you want. So again, you have another function pointer here to specify what to do when I'm in that state. And in this way, I can fuse the inputs together in a finite state machine. Okay. Now, if the output function returns a dwell state, okay, then I could use my interrupt system again, where the interrupt service routine would execute the available input functions one and one until it comes a true. Once I find a true, I go to the next state. Once I'm in the next state, I execute the function associated with that state. That function returns a dwell time, And that dwell time then is set up in the interrupt service routine to specify how long to remain or dwell in that state. All right. I got halfway through. Yeah, I did 2 of the 4. Okay. What we'll do next is we'll do 2 more. Fuzzy logic and performance maps are the other 2 methods we're going to do, which we'll pick up on Tuesday. And then, like I said, what's after this is we're going to talk about the actuators, and then we'll go into the next chapter, which is the theory of communication. So actuators in power are the remaining 2 topics here in chapter 3, or whatever chapter number this is. All right, any questions? Okay, so I am, so I'm actually ended early today. So let me review what was the most important thing about today's lecture in terms of sensor fusion. All right, I didn't get a chance to say it, but the most important thing about this lecture is actually the last lecture, okay? And you can't fuse sensors together you don't understand, okay? Now that we are fusing the sensors together, we're fusing them for a purpose, and so you got to understand what your problem is. So again, the second most important thing about this section is the next lecture, which is on the actuators. The reason why I give you 4 possibilities is because, you know, I don't want you to necessarily choose the only one you know about, but enjoy teaching yourself something new, right? Teach yourself neural nets and see if it will work. Teach yourself fuzzy logic or performance maps or whatever. We're going to get to those 2. Okay, so questions? All right, so okay, so we do have some office hours tomorrow. Again, the 7 o'clock office hour I've opened up to virtually anybody on campus who wants to ask a general question. So if you'll show up on Friday at 7, there'll could potentially be random people in there. If you show up during a 319K student, yeah, please help me teach it to them. Because sometimes your perspective is way more interesting than mine. So, yeah. Any concerns or questions?
You might want to add optical encoders to the sensor list next time.
All right. And what do you give me an example of an optical? Oh, you mean like the infrared? Yeah, the black white things. Yeah, yeah, totally.
Yeah, instead of Hall effect sensors.
Yep. We used to do that in 445L. In fact, we used to do that in 445M too. We had black white printed things on the wheels, which is why I had so many of those optical sensors in my office. They were, just as troubling as they were in the.
I guess another thing is how many people here have taken 445L or 445M or 319K? Because I feel like sometimes you might be teaching a little bit to them, and I haven't. I mean, it's been 15 years since I was an undergrad.
Okay, so you think what I did today might have gone under their heads and over yours?
No, I just curious, like, how many people here have taken those classes and.
Okay, so yeah, obviously Rita and Corey and Caleb TA'd it. Keyshawn took them. Yeah, Ben took them. Yeah, Ben TA'd.
All right, I just don't want to be at a disadvantage because I didn't.
Well,
take-
it turns out I squared C is not something it showed up in 445M because we had the ST microsystem sensor and we tried to use it. But I squared C is something that actually hasn't shown up in any of those courses because I didn't like it. Yeah. Okay, so let me just charge everybody. Something that I said today, yeah, something I said today. Okay, so what I didn't do is I didn't show you any code. Okay, did I hit the, no, I got one more button. All right, so, okay, Google Drive, let's see, Dropbox, IoT. Now, are you more scared of I squared C or the A to D converter? Well, let me do I squared C. If you go back to the whole point is you want to be able to find yourself a set of starter codes. I don't expect anybody in this class to understand how this function works. In this class. Yeah, if you were in 445L, I would. Okay. And similarly, I don't expect you to necessarily understand how this works. But which of the files in the universe did you have to understand in order to use it?
The
To
header
change
file?
it, yeah, I'm sorry, yeah, header file. Yeah, thank you. To change it, you have to understand the C file. But to use it, you have to understand the header file. All right, so the question is, can you understand this? Okay. Prescale of 30 means 400. Can you understand what 400 kilohertz means? I mean, that's the I squared C clock. Okay. Can you understand this function? Okay. Okay, this one's a little bit, that one's a little bit complicated because that one sends a whole array. How about that's in a whole array? How about this one? Okay. Can you understand this function? Receives 1 byte from the device at that address. Sends 1 byte. Sends 2 bytes, sends 3 bytes, sends 4 bytes, etc. So in order to use the stuff in this particular class, you really got to know your way around the header file. So let me do it again with the with this guy. Let me do it with interrupt trigger because that's more fun. Okay. All right. So, and you can see there's a Doxygen file somewhere if you don't even want to look in the header files. All right. So, do you think you could figure this function out? Yeah, I'll let you read it for a moment. All right. What do you suppose task is?
Pointer to a function.
Now, whose function, mine or yours?
Mine.
Your function, okay? And what are the inputs of your function?
Result. ADC result.
Yeah, the 14-bit ADC result, okay? What do you suppose this is?
Period and units. 1 over bus clock.
Yeah, of how fast your A to D converter is triggered. That's the sampling period. You think you could use that function?
Yes.
Yeah, so I expect you know what an A to D converter is. I expect you know a function pointer. I expect you to know the Nyquist theorem. But it turns out 319K, 445L, and 445M didn't use this processor. This is an MSP 432. But, okay, and yeah, look, how many functions do you have to know? Not very many, okay? Yeah, this one's all full of this one's interesting. Look at this one. So I'm just trying to belay your fears, okay?
I guess that was more like the specific implementation of certain things.
Yeah, I want you to know,
But
yeah, I don't know. You're not writing C code that implements I squared C in this class. Unless you do something stupid, like use a processor that has no libraries, in which case then you are. But I expect everybody to use the libraries. I'm sorry, did I make you more afraid or less afraid?
no, I'm not worried about the labs. It was more the test, questions. Are they going to be
Ooh, yeah, sure.
your prior?
Okay, so let me ask you a couple of. Let me just ask you a couple of. Okay, so let me ask you. What do you imagine I'm gonna ask based on the lecture we just did today?
Central limit theorem.
Yeah, central limit theorem. What are the assumptions? How does it use? What does it mean?
Averaging sensors.
What's that? What something that's not central limit theorem?
State machines.
Yeah, that might be fun. Like you could actually implement, I give you the structure and you could actually write me the state machine. That would be fun. I give you the structure and the data structure and have you write the state machine. Again, it has IO, but it's not part of I could ask that. Or I could give you a different problem and have you write the struct for the state machine.
That sounds 319K-ish. Could we stay away from that?
Yeah, I don't know. Probably don't. That's not what there's one that I'm going to ask. Obviously, we didn't do it. Okay. What here on this page that's on here that's not central limit theorem? There's another word here. Probability mass function. Okay. What is it? Okay. State machine. Okay, it was actually in the other one. It was today, but it was the other. It was on this picture. I could ask you this. What questions could I ask out of this? Let's say I gave you the picture. What could I ask?
What protocol is this?
Yeah, I could ask what protocol it is, sure.
How to calculate energy?
Yeah, energy. Yeah, I could ask you the energy equation, the energy thing. Okay. But it'll show up big time in the next chapter, so you'll get a chance at it again. We already talked about it here. I could ask you, how many pulses are there?
Ten.
Were there 10? I think there were only 9. 1, 2, 3, 4, 5, 6, 7, 8, 9. There are 10. What's up with that? Okay, whatever. Oh yeah, I know. There's 10 because there's. Okay. I don't know why there's 10. Okay. The point is embedded in here is the word bandwidth, right? How much information is being sent. I'd have to tell you, let me go to this one. Where was it? That one. I could ask you bandwidth. Okay. What's the bandwidth of this protocol? What does it mean? And what is it? And by the way, it's listed on the bottom of the curve, right? What's the bandwidth is the ratio of what two numbers? You see it right there?
Data and time.
Yeah. There's a lot of bits here. That's not bandwidth, that's bit rate. Okay. That's the thing that's 300 bits per second, 300,000 bits per second. But bandwidth is the total information, which is, 1, 2, 3, 4, 5, 6 bytes of data in this protocol. The other 6 frames, if you'd like, are just overhead in collecting that data. Okay. And the whole thing took 400 microseconds. That's the bandwidth.
Would you tell us what the, writing to the slave address, writing the address, and like, how do we know there were 6 bytes?
I'd have to. Okay, so I would give you a different one that was clearer. Let's say I gave you this one.
There's 1 byte. Out of
There's
the,
1 byte of data, and I'd have to give you the time.
overhead.
Yeah, packed with all that other crap. Oh yeah, that's where the 10 is. Right. I forgot the start. There's a start and a 7 bits of address, 1 rewrite, and the acknowledge. That's where the 10 pulses came from. So
Okay.
I don't know. Yeah, sheesh. But hey, Keyshawn's got you covered, right? What happens if you really bomb a first exam, Austin? What are you going to do?
Lab 5.
You're going to do lab 5. Okay, how's that? Thank you, Keyshawn. Yeah, what are you going to do if you do well on exam 1 and 2? Do you do exam 3? Do you do lab 5? Maybe not. Okay. You just sort of trust you've got it. All right. Yeah, this is only one of 10 chapters, right? So most of the stuff we're going to do is not 445L, but we are going to actually write code, and that's why I put it out as a prerequisite. I want you to write code using the libraries. I don't know. 10 years from now, the students will have no trouble because there'll be 10 years of exams for them to study. But yeah. Fundamental principles, where I'm going to go from. And, I don't know. I probably run them all open book. How am I going to keep you from looking at stuff? I can't. All I got to do is keep you from talking to each other by looking at your faces, right? Any other questions? I'm going to stop recording.
I had a quick one about whether the slides would get